I'm back here into the main site of the UAVSAR application notebook page. And now we're going to take a look at the level 1B and level 2 products, which are the interferograms. And these interferograms, just to give you a quick overview, is the information or the images that we used to generate the time steps that we just took a look in the previous model. So the interferograms are basically the measurements, the actual measurements that we took to, or that we generated to basically form those time steps. And I'm gonna go quickly over them. I'm not gonna expect you guys to run everything, but I think it's important to show them and for everybody to know that they are also available if anybody wants to play with them, and that they were used to produce the level 3 results. So we can go ahead and open the level 1B, level 2 UAVSAR notebook. And once again, we see a very familiar set of instructions here. So please just select them all. And remember, command and slash or control and slash, depending on which computer system you have, so that it looks like the example that I'm showing in the screen. Remember that when the instructions are active, they show some coloring depending on the script. Once everybody's ready, we accept, and the usual permissions allow. Connect. So if you connected successfully, you should observe a mounted drive. Hopefully everybody was able to do it. And just the same information. Remember that these data sets can be found. We have the reference here, as well as in the main site. So just like before, if we open, we're going to be able to see level 1B and level 2. Oh, sorry about that. And level 2. So what is the difference between level 1B and level 2? The difference is that level 1B don't have geographic projection. So they are only in pixel coordinates, and they are also in the viewing format of the aircraft. So these products are a little bit less friendly than the ones that I showed before. They can be also open in QGIS, but they won't have a reference in this case. If they look like this, you can see how they just look like rectangles because they don't have projection. So this is a previous step. We have them like this because it makes it easier to work with them. And then we can, once we are done with this level of processing, we can geocode them, and then we do the other parts of the processing. But we still share these products as a possible download if people feel comfortable working with them. The level 2 is the same type of image, but they are geocoded. So these ones can be displayed in QGIS. They have the proper latitude and longitude reference WGS 84. So just so that you know that if you feel curious about these data sets and you want to open them in QGIS, they both will open, but only the level 2 will be referred to the actual latitude and longitude. The level 1 will be in dimensions of pixels. So just be careful when you open those, and make sure that you are opening the one that you actually wanna visualize. So now, what is inside these level 1 and level 2 products? Well, these products are the interferograms that were used to generate the wire level change derived from InSAR. And basically, it's conformed, each set of images is conformed by 4 parts: the amplitude, the interferometric amplitude, the wrap phase, the coherence, interferometric coherence, and the unwrap phase. And the most important part is the wrap phase and unwrap phase, because these are the 2 sources that will tell us the surface change. The coherence is a layer that helps us to define which areas, when we compute the interferogram, between those acquisitions, which areas had too much change between them, and that we could not really make a good comparison between those images. So for example, in this case of this example, this coherence, we call it a spatial coherence, and is related only to the interferograms. And every interferogram has one coherence, one file of coherence. So one package of the interferogram for level 1 will be all these 4 images that you may want to take a look at. And the importance of the coherence is that it'll show us, for example, areas that suffer a lot of change in between acquisitions that in the interferogram then we couldn't really capture well, and they become or start becoming noise. So for example, you guys can see that in this part of the acquisition, we see how in red, most of the part of the wetlands, it's okay. It's value 1, which is good coherence. However, we see how it drops towards the bottom part. This means that there was something, it could have been rain, it could have been water level too high that covered the vegetation, not allowing us for the double bounce, or simply like some factor that change the features on the surface that we are observing, that changed them too much, and we couldn't really do a proper interferometric process in that area. And we can also mask them based on coherence, mask the pixels based on spatial coherence. And this is, again, this is just so that everybody knows that it's available, it can be used. But the most important product is the level 3 that we just went over. So then again, a little bit of the same guide that we just saw, how to access the data. We've just been looking at this exact same site where the documentation is located. And we go back to how the InSAR works. And just to iterate on this part, again, we have 2 passes of the sensor, and we take the difference of the phase between those 2 passes to be able to determine the little shift between the phase and see how much was the surface changing, as this figure shows. For example, this figure shows a drawing of a possible volcano or a mountain, right? That change downwards. So that is the change that in this figure is being quantified. In our case, what we're quantifying is water level change. And just remember that, again, for us to see water level change, we really want the vegetation to be there and to have double bounce so that we can get signal back to the sensor. And again, the example that we've seen before, where we can see how the satellite shows low coherence, because there's low coherence in the delta, we have noise in the interferogram in the delta-X area. But with a data set like UAVSAR, we have good coherence in the delta area because we have a very fast revisit. So the delta is clear in this type of data set. So just keep that in mind. If you ever happen to work with satellite data and expect it to look like this UAVSAR data set, it won't look like that. There's a very big difference just because of the revisit time and how the vegetation changed in those the water as well. So, and again, remember that this is the map of the coverage. So we have the same coverage, just instead of time steps, these are interferograms. And then just so that the processing of the interferograms is a little bit understood, for each acquisition, for each pair of acquisitions, we can generate one interferogram. So we took all the set of acquisitions and we generate a set of nearest neighbor, which is the closest acquisitions in time, then nearest neighbor plus 1 and plus 2. So one date is related to 2 more dates to generate 3 interferograms, basically, that are related to one date. And with this, we then estimate changes in the surface. This is how the interferograms look like. The amplitude, what it shows us is the back type of case. It's not used for the processing, but it's useful because since it's black and white and it's related to backscatter, it's very useful to locate yourself, to know where the interferogram is having signal of some type of signal or feature, so that you can kind of like visually also orient yourself, but it's not used for the processing. The wrap phase is the actual measurement obtained from the interferometry. This is the product from comparing the 2 phases of the acquisition from the UAVSAR or a satellite, depending on what data set you're looking at. Again, the coherence is the correlation between the 2 images that we are comparing, and it'll help us to see which parts had changes over the two acquisitions. And the unwrap phase is basically the wrap phase that has been already translated into actual dimensions of change. And I will talk a little bit more on that because it's a complicated concept, and it's just an overview. It's not important to understand it fully, but just bear with me a little bit because it can be a little bit difficult. So an interferogram captures the changes in cycles of 2 pi. So we have a wave and it goes down and comes back, and what we capture is how the wave change in terms of 2 pi. And that will be a wrap interferogram. But a wrap interferogram, even though it can show, this example is of an earthquake. You can see here the wrap phase in the top. What the wrap phase shows is the actual deformation, surface deformation that was captured by the sensor when we compare the 2 acquisitions. But it's from 0 to 2 pi. So we now need to quantify those cycles of pi to actually say, okay, we have a total amount of change of 10 centimeters, 20 centimeters. That's why we need to do the unwrapping process, which is basically we grab the wrap phase, we unfold it. You see here how this fraction went all the way from 0 to 8 pi, and then went down from 8 pi to 0. And this is the change that was captured in that little segment of pixels, for example. That is what the process of unwrapping is. We unfold the signal so that we can actually quantify the amount of change. And then we're going to use all those unwrapped interferograms to create the time series. Alex? The gradient just represents like change. It's just for pretty. But
the question was, what does the color represent in the left plot?
Yeah, it just represent, basically, the idea is that because in the map, in the wrap phase, the formation we see it as something we call fringes. So, and it's like these rainbow kind of like looking things. And these rainbow things are the actual change that was measured in the surface, and that needs to be quantified. So this little drawing is just trying to represent, okay, these were the fringes. And then we went from 0 to 2 pi. So 0 is blue, 2 pi is red. And we see those fringes. And then again, the fringes. It just represents the colors here, but it's, yeah, it's just for like as a visual aid. But in the map, the colors in the actual interferogram here, the colors represent change, surface change. So everywhere that you see these rainbow-looking things, it's because the interferogram was capturing change in the surface. And when it's unwrapped, this set of rainbows here, when it's unwrapped, it looks like this in the bottom. So you can see how after the quantification of all those little series of colors, you can end up with a full set of displacement map for that specific interferogram, right? For that moment in time where you took acquisition 1 and acquisition 2. You then need to do the series of interferograms that you're going to use to generate a time series.
Can you repeat it?
I think maybe it's very complicated to explain what actually happened between this unwrapped and wrapped, like this technical question. But on this picture on the right side, we have this two picture. The two picture on the top is the wrapped one. On the bottom is the unwrapped one. So maybe the unwrapped one is the raw data. So after
it's the same data.
Is the same.
So, it's the same data. Imagine that you. I don't have it.
So after some processing, you change this wrapped one into the top one to the unwrapped.
So imagine that the image was like a folded page, and you had to stretch it so that you know how long the page is. So this part is the wrap phase, and we need to stretch it to measure how much the change was in that particular time, so that we can then connect it to the other images and know the progression of change in time. So we unfold, the wrap is just a series of changes in the signal. The unwrap is we grab that signal, we stretch it, and then we measure the change using the unwrap. So the interferogram is going to give you this type of information. Wrap, folded. Unwrap is a process that we need to do. We need to compute it. We need to quantify it so that we then know, okay, how much the displacement actually was.
Okay, thank you. I'm clear.
Yeah, I don't think we expect everyone to learn everything about InSAR in this one presentation. So,
and just a last thing on this process, I mentioned temporal coherence. We have a temporal coherence map in the time steps. That map, what it tells us is how well we did our job in quantifying, in actually unwrapping our signal. So that's why it's useful in the time series, because once we unwrap all our signals, we then need to know how well we did that job. And that map in the level 3 product is what it tells, the one that tells us how well or how bad each pixel was unwrapped. So, but yeah, don't dwell too much on it. It's just part of what it made possible, the measurement that we show previously. And then again, how to download the data. We go to the link in ORNL. We can search also on the search bar. In this case, we can download an interferogram that corresponds to the data set that I showed before. And be careful, because now we have obviously way more images, right? Because we did connections with nearest neighbor plus 1, and nearest neighbor plus 2. So for a set of let's say for the whole West Terrebonne, if we go to the summary, West Terrebonne, the flight line 34202, for April 5th, we took 8 acquisitions and we generate 18 interferograms. So 18 interferograms are available for the 8 acquisitions that we collected with UAVSAR. And these 18 interferograms, all of them are maps of change from the surface that were estimated by comparing these 8 acquisitions against each other. So characteristics of this data set, it's very similar to the data set before, binary in NV format that can be opened in QGIS. Remember, level 2 is geocoded, level 1B is not. The pixel size is similar, 6 meter. Temporal coverage, it covers the same temporal as the time series. So we have one spring, one fall, being a spring for March 27 to April 18, fall September 5th to September 13. And acquisitions approximately 30 minutes apart. Now the naming convention for this type of product, it's also very similar, where we start with the name of the flight line, the number of the ID, the number ID of the flight line, and then we have date 1, date 2, the version, and the type of product. And this type of product can be then the phase, the coherence, the amplitude. So for example, here, if you see here, we can have interferometric, the interferometric product. The COH is coherence, interferometric amplitude, it'll show us int amp. The phase, it'll show us int phase. And the unwrap phase, it'll show us U and W phase, unwrap phase, so that you know which one you are using or displaying. So the examples here are gonna be very basic. We are not gonna compute an interferogram. We are not gonna do unwrapping. We're just gonna visualize the data just so that you guys know how it can be manipulated. And that's all. So we only use these libraries, NumPy for arrays, Matplot for plotting, GDAL for raster handling. So we can run this cell. And remember, before running the next cell, we have the comment. Are you running using a Google Colab? Yes, we are. So let's uncomment this. And let's comment the one below that it's for running on a local computer. So, and what am I doing in this cell? I'm just inspecting again what is inside the folder and what is inside the L1B in this case, just to take a look. And just as we saw before in the other exercise, I'm going to use GDAL info to see the information of this raster. So I run this. So we see what you guys already know, which is what is inside our data folder. Now we want to take a look at what is inside L1B. Okay, my sample data set of L1B is here. And you guys can see that in blue, I have a coherence file with the HDR, that is the metadata reference file. Then we have amplitude. Then we have phase, interferometric phase, and unwrap phase. So this will be one full set of interferogram data. And then what does GDAL info provide about this? So we go ahead and just do GDAL info over one image. In this case, I chose the interferometric phase. So we see that the size is 3,300 by 10,000. We see that we don't actually have, as I mentioned, we don't actually have a geocoded kind of like reference. And then we have just the corner specifications, as well as the format of the data of this raster. So we can just go ahead and load the data just as we saw before. We use GDAL open, and we specify the path to each one of the .dat image. So if I run it, it's gonna load our images. And then this little part here in the bottom is just to, again, print some information using GDAL so that you know that you can use it if you need it. But it's not super important right now, but it's just, again, we don't have projection, our dimensions in X, Y, and we have only one band in this product. So, okay, let's go ahead and start taking a look at our data. Let's plot the coherence, the interferometric coherence. So you guys can see that I specify coherence, and I say, yes, this is the coherence. And I'm also gonna plot the histogram of the coherence. So here we see the map of coherence for this specific interferogram that show us how the two acquisitions, where, more specifically, where was the variability areas between the two acquisitions. And then red are values of high coherence, just like in the other temporal coherence that we saw. It's just that this is spatial coherence. And 0 are low values of coherence. So you can see that, as I mentioned before, water is not very good for this type of process. So water is very low coherence. So we should be thinking of masking it out. And then we have some areas that are so kind of like yellow. And this is probably because there was some inundated regions, right? So there's some vegetation that is covered, some vegetation that is partially exposed. So we have variability between those two images, and it creates this type of figure. And then we just can see in the histogram, it helps us to see what is the distribution of our coherence. And this is useful because we can play with these thresholds and separate the water using our histogram. In this case, we know that the water is mostly located in this lower part of the coherence. So we can threshold it, create a mask, and get rid of that water. But first, let's take a look at how the wrap phase looks like. So just to warn you, here I'm gonna plot the interferometric amplitude for visual aid and the wrap phase. So you're gonna see both the amplitude and the phase. This histogram is phase histogram. And as I mentioned, because this is wrap, the values go from, in this case, it could be 0 to pi or it could be minus pi to pi. It's just where, I mean, it's the same, it's just where the center is. In this case, it's minus pi to pi. And you can see here how the wrap phase for this interferogram look like. And in this case, just the backscatter, just as a visual reference, so that you know what are we looking at, because these maps can be a little bit tricky to observe. And you can see how the water, it's very hard to differentiate. It's really, you cannot even see anything that makes sense within the water. It's all kind of like noise. So really, we should mask it out. It just brings noise to our measurements, and we don't get any information from this part. However, we do see already from the wrap phase, we see areas where we detected change. We see some that is atmospheric and some that is actually water level. But this is the actual main source of change information that we generate to then reach the level 3 data that you guys saw in the previous example. So a set of images like this help us to measure the change in time. So now let's take a look at the unwrap phase. Now you can see how already in the histogram it changed completely. It's not anymore between pi to pi. However, it is in radians. The units of this is radians because it hasn't been translated into actual displacement. For that, we need to take into account details of the sensor that was used to translate the signal into actual surface displacement, just so that you know that. And you can see the difference. This is the same data, just one has been unwrapped and the other one is wrapped. You can see how the value, the range of value is different, and you can already see how the map looks different. The direction of the change even is quite different. But let's just go ahead and mask so that we can better look at what we are observing here. So we generate, in this case, I'm just generating a set of masks just to play around. You can do your own, you can play around with this and play with water masks. You can also use the coherence and track down how the water change. It's another thing, a possibility, because we can observe it, we can separate it. It's very clear, the water. You can see here the noise, so it's something that it can be done, but you need to be comfortable also with this type of data. So we are now plotting different thresholds of mask so that we can see. So for example, this first figure, this is a very high coherence set of pixels. In fact, I define it as the pixels that are above 0.9. So these are the pixels that are above 0.9. And as you can see, and you saw from the previous image, the bottom parts of this image were kind of like low coherence. So that's why we kind of lose them. Those areas had some change, and if we use a very high coherence map in this case, we are gonna lose them. Now, if we have a low coherence, then we are gonna have a lot of noise from the water, and it's gonna make difficult our process of unwrapping and interpretation. So we can find somewhere a middle ground. We can play around. This is gonna be variable in each interferogram. There's not a single number as a clear threshold. This can be, depending on the data set that you use, these values may vary. Coherence will vary depending on the revisit time. So in this case, we have very high coherence because we're using UAVSAR, and the repeat time of observation is very short. But if it was satellite, this value range will be quite different. And maybe we will see all noise. And the areas that we actually see with high coherence will be maybe very small. So just keep that in mind. This map will change dramatically depending the type of radar that you use. But thanks to this very unique data set, we have very good coherence in this data set. So we are able to very nicely separate the wetland area here shown in yellow. So how does it look if we mask out the interferograms using our new mask? It's not perfect, as you can see. We still have some sparse pixels. That's okay, but now it makes more sense. We actually can see better the features where the phase is changing, both in the wrap and in the unwrap. So that's great. And this is very helpful for when we are interpreting and quantifying the change. And just similarly to what we did before, we can plot profiles of this using, in this case, because we don't have a geocoded reference, we just use pixel reference. And we can see the pixel reference from our previous plots. We have the reference there, right? We see that we go from 0 to 10,000 or a little bit more than 10,000. And then from in y-axis and in x-axis, from 0 to a little bit more than 3,000. So we can play around with those and create profiles and slices of the data if you are interested in what's going on in the interferograms. And that's what we do. We're going to create some slices and profiles of the data. So we run this cell. You can see that I generated here in the top of the code, I created horizontal profiles and vertical profiles. And just basically you choose, in one case you choose change values in X direction and change values in Y direction and stay at some point in X, or change values in X and stay in Y. And this is how it looks. So these are two profiles that we can subtract and take a look at the phase changing in those areas. This same method, we just use it for the time steps. So we are just exactly plotting again the same, and then we just plot the profiles. And then we can see in this case, differently from the other plots that we saw from the time steps, these plots show more variability. Of course, wrap phase, always within pi, and wrap phase can have larger changes or smaller, depending, but it's not constrained to pi. And the zero areas are the areas of open water. So you can see in the center parts, this, for example, this kind of like U-shaped thing, it's probably an area where there was an open body of water. And then we see the phase going up and down, and just remember, this looks like that up and down because we haven't really quantified the direction and the amount of change. So this still needs to be interpreted. But this is the actual signal that we use to generate those maps that we saw before. So, and then just what is the difference? The L2 interferometric products, very similar characteristics of the L2 interferometric products, similar naming convention, same pixel dimension, same coverage. The difference here in the naming, you're gonna know that it's a geocoded because it has this, .grd. So the products that we are delivering that have the geocoding coordinates have the .grd. And these ones are friendly with QGIS. You can open them, you can compare them with the satellite background map and play around with it in QGIS if you want to. But the data is the same, it's just reprojected. And then you can just, well, this is how you download it, we've seen that. And then you can plot it exactly the same. So this is just, the delivery looks exactly the same. One set of unwrapped phase images is just the GRD. One set of interferograms, GRD, interferometric amplitude, geocoded, and interferometric coherence, geocoded. And you can see that when I use GDAL to see the metadata of this image, now it's way more rich. Why is way more rich? Because now we have more information. We have the geocoding information. So similar to what we saw before, right? We can see the ellipsoid of reference, the coordinate system, and the corners of the image that then we can use to reference our plots and our maps. So we can go ahead, read the images. And then we can see that now when we look at the geotransformation information, we have information for the geocoding, right? And we have the corners of the images. So that's great. We can then now plot them using the same feature that we saw before, where we can extract the specific corners of a raster just by knowing the length and width, and this geoinfo here, where it tells us where the corners of the image and the pixel spacing. We use that, we estimate our corners, here we are. So now we can take a look at the geocoded plot. This is how it looks, but the data is the same. It's just projected, right? So same information, and same information for the phase and for the amplitude. It's just that now it's projected. You can see that now the axes are latitude and longitude. So just use the data set that you find more convenient. Be aware that because this one is projected, it's larger file. So just, it's not exactly the same size of file. These geocoded products are a little bit larger in size. So just that in terms of computing, if you have like a small hard drive, just keep that in mind. And then again, we can compare the wrap phase with the unwrap phase, same data, just with the projection and our masks, right? So we generate our masks, but nothing really changed except that I forgot to read my geocoordinates. Here, sorry. You see, because I put the geocoordinates here and I used them later for the plot, it gave me an error. So I went back, I run it. Now that my geocoordinates are run and are there, I can come back here to the red one and run it. And now it's gonna know. So our mask, same, just that now it's projected. And it's basically the same type of process that we did. It's just that in this case, we need to keep in mind the same things that we did for the time steps, which is we play around between pixel coordinates and latitude and longitude so that we can play around with the map and the plotting of the profiles. So we just mask out the water pixels, and maybe it's gonna crash. You can see here, that's why the plots, because the data is too large, you can see here the RAM. It's consuming quite some, so hopefully it doesn't crash for you, but if it does, don't worry. The figures are there. This is just to show that we mask the same way. Everything is exactly the same, just we now play around with pixel coordinates and latitude and longitude. And just like we did before, we can then grab our sample, transform latitude and longitude to pixel coordinates so that we generate profiles of the phase, if you happen to be interested on that. Of course, most of you are just gonna be interested in the level 3 products, which are already digested into water level change. So yeah, you see, I got an error because I'm using too much memory. But it's okay. This is just the last part, thankfully. So that's how we can inspect and handle the interferograms. So again, this is just an overview. It's not necessary. The more important product is the level 3, but it's important that people know that this is useful, that it's there, that you can use it if you want, and if you're interested in looking at it. And someone had a question that I just saw popping up.
Yes, we have a question online. What is the purpose of carrying forward the wrapped phase throughout this analysis if the unwrapped phase is what is used to get metric units? Also, the unwrapped profile plots are also in radian units. What is the process for converting those to actual elevations?
So the reason why we keep the wrap phase is because it's the original source of information. So if someone really wants to work with it, it's there, it's available. There's people that may want to be working with the coherence, or they want to do maybe their own unwrapping. So it's available there for people that feels comfortable playing with that, and that maybe they don't want exactly the product that we deliver, they want to do something else. And that's basically one of the most important, is basically after the acquisition itself. And then the unwrapping, yes, it still looks a little bit difficult to understand because it's in radians. So depending on the wavelength of the sensor, in this case, we are using L-band, which is around 24 centimeters. We then need to translate these radians into distance. And it's just a process of relate these radians with the wavelength and then the viewing angle of the aircraft. And then we can transform into actual dimensions, but it was, or I thought it was a little bit too deep into the bones of the InSAR to touch those details. But it's just basically, we relate the unwrap phase to the viewing angle of the airplane as well as the wavelength that the sensor uses. And then we translate that into the actual dimensions of metric changes. So yeah, and this is how they look. That's a very good question. So someone asked, what is the control of the aircraft to do an effective phase difference? And I'm not sure that I don't know if Kathleen want to take over because she's more versed on those details.
Yeah, UAVSAR is actually a combination of the instrument and the aircraft. The instrument measures the position of the aircraft and feeds back to the control flaps on the aircraft so that the plane flies within 5-meter tube of, and then in the processing, we measure the position of the aircraft and we remove that component from the phase whenever we do the processing. So it's actually a much more difficult processor than for a satellite because a satellite doesn't move all around all the time. Yes, yes.
Question is if it's using kinematic GPS, and the answer is yes.
I'm sorry, I couldn't hear you.
Just repeating the question.
Any other questions?
I heard Alex here in front.
This is maybe a question out of the topic. How did you add projection to the level 1 data to get the level 2?
Oh, sorry,
How did you add the projections to the level 1, L1 data to the L2, to get the L2 data?
How do we project? So part of the delivery that UAVSAR collects all this information and they use a pre-processing. I'm not part of that specific, so I cannot tell you in details. But the delivery, if you download the L1, which I'm gonna go very, very, very superficially because it's even more difficult than this one. But that one contains latitude and longitude files of the acquisition. So you can use those files to project correctly so it's part of the L1 delivery, the coordinate files. Yeah.
Thank you.
So yeah, if you want, I can just move to the L1. It's gonna be even shorter. It's just gonna show how does the actual radar acquisition look like. And that's basically the basic level of the InSAR processing. So before even generating an interferogram. And I'm just gonna show that so that people know that it's there. I understand that not everybody's gonna use it, but it's also a product that people can download and play around if they feel comfortable with it. So let me just get out of this notebook and go back to the main. So we go back to the main link, and we're just gonna briefly brush through the level 1, which is the acquisition itself of UAVSAR, so that you guys know how you can plot it if you want to, and how does it look. So we can open. Again, we have the citation, and we can go to the OR now. Just close all these ones. Yes. Close this. So the UAVSAR level 1, also known as single look complex, SLC. these are delivered as a stack, that it's co-registered, which means that the images are already well overlapped on top of each other, so you can actually match them as a stack. And it's just a set of the geometric files that we use for the projection. As you were asking here, we can see LKV, LLH, some information about the sensor that is needed for properly reading the image, an annotation file that is .ann, and the SLC. And then each one of those SLCs is 5.5 gigas. So that's one acquisition of the UAVSAR. So this is really, really the kind of like the bare bones of the data. So from this, you can go all the way to level 3 if you want to, and just know that this is the source of the level 3. But of course, you don't have to use it. It's very raw data, just for people that wants to play with it and feels comfortable. Sorry. So did I close the notebook? So let me open the notebook. So just again, in the notebook, we uncomment so that we can connect to Google. Connect to Drive. Okay, so everyone knows already, once it's mounted, we are ready to go. And then just the first part as an introduction, you guys can take a look at any time that you want. It's just how to sign up for ORNL, how to get the data, where to find the data set, how does it look, and the coverage is the same. Now here we have the basic information for an acquisition. In this case, I should mention that some of these images of SLC are divided, just so that it makes an easier to handle type of file, but they can be just put together one by one very easily, and I'll show how. But we call that segments. So it's just basically one full image that was divided in two, but it just corresponds exactly. It matched perfectly, pixel by pixel. So you don't have to worry about any sort of processing. You just match the last pixel of the segment 1 to the first pixel of the segment 2, and there'll be a full image again. Sometimes people just are interested in a single fraction, so you don't have to download the full SLC. So once you chose your data set, if you want to download, remember that you may receive an email that will make easier the download by batch download. And then just some details about this data. The pixel resolution here, it's a little bit different. It's not exactly square. It's 0.8 in one direction and 1.7 meters in the other. So it's very high resolution, and it's not square. The other data sets that I show are squared because we already adjust the pixels. So that one is 6 meters approximately square pixel. This is not. So just be aware of that, and it's very high resolution. That's why they are very heavy in terms of size of file. And just what is the basic information in the stack? As I mentioned, the SLC file is the main image, the annotation file, as well as reference geometry files. and Doppler files, which are just important for when you are handling the image. So this is just going to be on how to read it, visualize, and just do a couple of plots. Nothing too complicated. It's just for everybody to see how the actual acquisition looks like, and that's it. So we can run the libraries. You are probably already familiar: NumPy for arrays, Matplot for plotting, and GDAL for raster handling. The second part, again, you are very familiar. We uncomment the work directory so that it matches our Google Drive, comment the one that is the local, and we can inspect what is inside this folder. So we go inside the, that's interesting, why? Let me see. Yeah. UAVSAR 3 data. I didn't upload it, that's why. I forgot about that. I was not planning to run it, sorry about that, because it's very heavy. Yeah, so don't worry about it. This is just if anybody wants to do it locally, because yes, each one of these images is about 5 gigas of size. So of course I didn't upload these files, so they are not available in the drive. So of course it doesn't find the file in the drive. But anyways, so if you, no, they are not, they don't exist in the, no, but B, remember L1B is an interferogram. So L1 is an SLC. No, it's my bad. I'm sorry for the confusion. I didn't add those. I have it locally, but I didn't add those on purpose because it's too heavy. So let me do it like this instead, so that I don't mistakenly do things that I shouldn't. So I'm just going to show it like this. If only I click the right one. Level 1 SLC. My apologies for that. That data is too heavy and I didn't share it, and I didn't expect anybody to be downloading tens of gigas of data just for a plot. So yeah, so if we read the directory, it's going to show us how it looks. So in the case that you downloaded the data, let me zoom in. Let's say that you are doing this locally and you downloaded the data and it's UAVSAR L1. This is how it's going to look. An annotation file, an SLC segment 1, because this specific image it happens to be split in two, and segment 2. So we can see, we can plot what is inside the annotation file. And this is very nice, even if you are using other level of products, just because it tells you information of what makes the data set, the level 3 data set. This is basically what the source of the level 3 data set. So it's going to tell us all the list of acquisitions for all the stack. You can see that there's the information of each image. It's going to say pixel size, names. So the annotation file basically has all the information of each acquisition. And if you decide to play with this data, this is where you're going to find really relevant information on the data. You can see here size in pixels, dimensions, latitude, longitude files. So we are not going to go over this, just so that you know that it exists and is there in the level 1. And this is the main information of the metadata. So now, just to show you, if we were to read an interferogram, we define the columns and the rows, and we can read the phase and the amplitude. In this type of product, the phase and the amplitude comes So it's one single image. So to separate the phase, we need to do this operation to take the angle in radians, and the amplitude with, the amplitude is the absolute, and the phase is the angle to take the angle in radians. So this is how the actual acquisition looks like. So in one side, we have the backscatter of segment 1 and the phase. And you can see how a single phase looks all like noise. And this is because an isolated phase does not make sense until you compare it with another second phase of the same area. It's not until you do the interferogram and compare two different acquisitions that an interferogram starts making sense. That's why we need to do the interferometry and compare the two phases. But this is just to show you how it looks. Don't worry too much about it. And then the backscatter, also how it looks. And then this is just taking a subset so that you can see a little bit more clearly. This is the area in the backscatter, and this is how it looks in the phase. And you can see that the phase varies from pi to pi, minus pi to pi. And another zoom, in case that someone is interested to use this data. And then just lastly, if someone happens to be curious on how to join the two segments, I did it here so that you guys can copy it. It's just based on the information that you read from the annotation file. You know what is the size of segment 1, you know what is the size of segment 2, so you can generate an empty array and generate it here. And then you basically populate that empty array with the image. And this is the very long plot. But this is how the actual acquisition of UAVSAR looks like. Don't expect people to use this. It's just so that people know it's there. If you feel comfortable with interferometry, anybody online or any of you here in the room, you can download this data as well and generate your own interferograms, do your own unwrapping, and reach all the way level 3 if you want to. If not, there's also the level 3, and you don't have to worry about this data. It's just so that you know that it's available as well. And I think that will be it for my part. If there's any questions on this, I don't know. Yeah.
So for this merging together, you have this merged backscatter 0 to row S1. Why not is row S1 minus 1? Add tails, like after 6, generating a single array using acquisition segments. So at the second block, add tails, you have merged backscatter, and from 0 to rows S1, you put the backscatter segment 1 into this block. So why it's not 0 to rows S1 minus 1?
You mean this part? Here?
Just
This?
one line down. Yeah, here. Yeah, why the index is not 0 to rows S1 minus 1?
0 to rows.
Yeah, just add your cursor. So the index is 0 from rows S1. So my question is, why not rows S1 minus 1?
Yeah, it's just for indexing. I'm not exactly sure.
I think
Yes, it's just how like the arrays
yeah,
interpreted by Python.
Yeah, so in MATLAB, the indexing is 1. It starts at 1, so that's
okay,
probably
okay.
why. Yeah, Python starts at 0.
Even if it's starting from 0, so from 0 to rows S1, that's the total length is.
Sorry. It doesn't include the index for rows S1. It goes up until the one before rows S1. And so then when you start with rows S1 in the next line, then it starts from that. So it's everything up to that, and then
Correct.
from that one on.
There is an overlap because you are using the same index at the beginning.
Yeah, so that's just the difference in how Python reads the indexing, yes.
Yeah,
Well, and then ultimately we can check if there's overlap because if there was the error, we can plot the size and we can verify this size with the annotation file. Ultimately, if there was such a situation, we plot here the size, the array size that we are exporting. And if that's the case, we can go and verify what should be our size in the annotation file, if that is the case.
Yeah, the last index is exclusive. It's excluded.
Yes.
So we had an online question, actually re-asking the question from earlier about how to convert unwrapped phase in radians to an actual elevation value. Could you talk a little more about, I guess, about the details of how that's done?
So we need to get the radian that was collected from the unwrap, multiplied by the wavelength, and depending on the viewing geometry of the aircraft, we calculate the angle and subtract it so that we can then estimate an actual distance. I don't have a visual drawing. I could, if that person wants to learn more, email me and I'll send a figure with an actual drawing on how that is exactly estimated. I can set an schematic or the formula as well. Yeah.
Just in general terms, when you're processing, do you use the L2 just so that you can compare the data to the landscape to interpret what you're seeing?
Well, it depends on what you want to do. If I want to compare the data with the landscape, I will use the geocoded L2 or L3. However, when it depends what exactly is that you are doing. Usually in terms of processing, it's better to use the non-geocoded and just geocode at the very end, just because the file is slightly smaller. So it's just simpler. And then you just apply the geometric at the very end. But if you want to see each one of the details in the map, you can use L2, definitely.
And just a general question, like, because they deal with a big file size, pretty often looks like. So, and we know that we are limited by the RAM memory. So whenever you have a file size that's bigger than the RAM memory, how you deal with that? Like,
that is
yeah,
complicated. And thankfully, this data is still, well, the first thing that we do is that we, for the interferograms, we apply something that is called multi-looking. That it's basically, when we make the pixel square, we take sort of like an average of a certain region. So we make it 6 by 6. This already makes the file considerably smaller. So already L1B, L12, and L3, the file size is considerably smaller because those pixels have been reduced from 0.8 meters and 1.7 in each side to 6 meters. So that already has been reduced, makes easier the processing. Another thing that can be done that I hope you don't have to face because it complicates the processing, you can divide the image in pieces and process by pieces, or only process a region of interest. That's also a very common thing for when you are processing locally. You can do some of the things that we saw here, get a subset of the data and just process that subset. And don't use the whole thing if you are not analyzing the whole, so that you keep the least amount of, to do a bounding box, basically. Mm-hmm.